So we're waiting on two more, although one of the students hasn't accepted the classroom invite yet. So I don't know if they can even join today. Um, I guess I think we can just get started. The first bit is not like I have to deal with a bit of sort of administrative stuff before we get to the content. So hello. So first of all, some of you might not recognize me, and that's okay because I am a new teacher this summer for you guys. So my name's Bill. I should probably change my name. I realize my name isn't Bill on the Zoom thing. There you go. All right, my name's Bill. I will be teaching Introduction to Counting Probability. This class meets on Tuesdays from 4 to 6 p.m. Every Tuesday, and every Tuesday you will be assigned a homework. And you should try to do the homework. We'll talk about that after class. Yeah, hopefully you're all here for Introduction to Counting and Probability. Hopefully you all have your copy of Introduction to Counting and Probability somewhere, preferably in front of you right now because we're in class. Does anyone not have the book? Hopefully everyone has the book. You're right, because I will be assigning problems from the book, and it would be pretty helpful to have the book to figure out what those problems are. Okay, that's good. Looks like everyone has the book then. All right. So a quick little side note, a quick little note before we start Introduction to Counting and Probability. This has been a historically difficult class, or a hard class compared to the other introduction series, right? So there's four introductions. There's algebra, geometry, number theory, and then counting and probability. Out of them, counting and probability has been the hardest amongst students. So especially for this class, please, you got one of the most important things to get down is the fundamentals. And so if you're ever if you don't feel like you really have a solid grasp on a certain concept, please let me know, because otherwise this will just keep building up, right? Like with the things we're doing in the first few weeks are just gonna build up, are gonna get built off of and just keep going. And if you're not super familiar with all of them, then it's gonna become really hard. So that's just a little side note. Hopefully that doesn't scare anyone away. Counting and probability is obviously very important. But yeah, does anyone have any initial questions before we get started? I will take that as no initial questions. Okay. So let's talk about counting and probability. So obviously we can't really talk about probability without counting, for those of you who know a bit of it. So let's talk about counting first. So obviously you guys know how to count, right? Right? Who here knows how to count? Please let me know if you can count. Okay, Myron says he can count. Does anyone else think they can count? Aaron says, oh, Rocky can count too. All right, we got some people who count. You're all wrong. No one here knows how to count. I don't know how to count. Okay, so let's talk about counting today. You're all wrong, by the way. Yeah, I know. Sorry. No, you're all wrong. You guys can't count. I'm being serious. You guys don't get it. All right. So obviously, good. Yeah, you better be in this class to learn something. So let's talk about counting. Okay. So obviously, in whatever kindergarten or what preschool, whatever, you guys probably learned how to count like this, right? You do 1, 2, 3, 4. You know, you start listing numbers and you keep going up. You know, you go up until you're bored or you just don't know the numbers. But of course, that's not what this class is about. That's not what we're going to say counting is, right? Obviously, if I give you a list of objects, yeah, draw a few objects here, right? You can count how many there are there. You can say, oh, there are 5 objects there. There's a diamond, there's a triangle, there's a circle, there's a square, there's a diamond, and there's a heart. Obviously, you can say there are 5 things here, and then you could say you're counting them. Of course, that's a kind of boring problem, and we want to be talking about more complicated things, right? We don't, otherwise it's kind of like boring class. So, maybe I gave you maybe I give you a whole, maybe I did this, and then I also, I shaded, so I did another one. I did not put another copy of them, and then I shaded them in so they're different. All of a sudden, you guys would say, well, this 5 times 2 equals 10 things here, right? And already you're going beyond just going along the number line and picking them out, right? You could have said 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But hopefully you guys are smart enough to realize that I could just take 5 and multiply by 2 and do 10. Right? This is a little faster, just a little. And that's what this class is going to be revolving around. How do we reduce problems to problems we already know? Right? Here we were able to reduce this problem to something we understand, multiplication. And so that's where we're going to start. And the only thing that we have at the beginning is a list of numbers. Right? So we build off of the concept of counting from 1, right? Just like we did above in the very beginning. That's what this entire class is going to be revolved around. And obviously we're going to do things like add and subtract and multiply, and use all the other operations. But this is sort of the basis for all of our work in this class. Yeah, and with that out of the way, we can start counting. So first of all, let's think about, because we start with that list 1 to whatever we want. Obviously it would help to know how we can count those numbers, right? So I'm not going to write all the numbers out, but somehow you guys can tell me how many numbers are in that list I just created. All right, guys, it's not a trick question, I promise. Can someone tell me how many numbers are in the list from 1 to 20? It doesn't look like anyone knows how many numbers there are. Myron, thank you. There are actually 20 numbers between 1 and 20. Thank you. Right, that's sort of like the whole point of counting, right? When you count, you're giving each one a label. Oh yes, Rocky, you guys know how to count now, so you guys can leave now. Right, but if you think about what counting is, you're assigning a number to each element of this list, right? And you're like, okay, whatever the last number is how many there are, right? Obviously in this case, we've sort of used the numbers themselves as the indexes, right? But obviously if we go back to a triangle, whatever example, I just did the same thing, right? What we're doing is we're essentially labeling each one of these with some sort of indexing, right? And we're saying, okay, the last one's 4, so there have to be 4 of them, right? So hopefully that makes sense. And we can apply this concept to other lists of numbers too. So let's say we had the list 8, 9, 10, 11, all the way to 31, okay? And now we're thinking, right, how many numbers are here? We could count them, of course, but and we can start counting them, right? We can start labeling them using our little indexing property, and of course you'll quickly realize that a pattern forms, right? Every time we label it, we're just a difference of 7 between the index and the actual number we're counting. And so once we get all the way back to all the way to the end of 34, we'd of course expect us to once again be producing a difference of 7. So we'd expect this number to be 24, and we would have counted that, right? And of course we're already building off of the simple list from 1. And now we have like a list from 8 to 31. Of course lists get more complicated than that, and so it's best if we devise a formula for the more general list, right? So let's write that out. A plus 1, A plus 2, all the way to some B, right? And these are all integers. And they're consecutive integers. So if we do the same thing again, right, we start labeling them and we go along. We want to figure out what we should put here. And to do that, we do something similar as before, where we realize that the difference between each one of these is a minus 1, right? To get from 1 to a, you add a minus 1. You add a minus 1. So of course you'd expect a minus 1 to be here, which means that down here is probably something like b minus a plus 1. And this is your formula for counting lists of consecutive numbers that start and end anywhere. Pretty helpful. Of course, that means the answer is not b minus a, as some people, not b minus a. As some people like to think. So try not to make that mistake. But of course, we can do more complicated things than just adding numbers, right? We can, so let's say we had a list like, I don't know. I'll take the book's example. I'm not bothering this. Let's say we had the list 63, 66, 69, and then all the way to 213, right? Each time you add 3. Each time we add 3. So in this case, if we wanted to start this with 1, as we always do, right, and then 2, we could try what we did before, but of course we'll see that the differences are now different, right? We add 62 here, and then we add 64, then we add 66, and clearly it's not going to work, right? Because it doesn't really tell us what we should do here, right? So we're going to need a more sophisticated method of counting these, and it turns out it doesn't be that sophisticated, right? So we realize that these indices are currently going up by 1 each, but the numbers themselves are going up by 3 each. I'm gonna probably write that out. Plus 1, plus 1. So it would help if we first maybe multiplied each one of these numbers by 3, right? So it's called n, 3n, right? And if that's the case, then all of a sudden we're doing a lot better, because now the difference is always 60. Right, and so it turns out that if our general idea of what we want to do here will be to multiply by 3 and then add 60, and that's how we'll get from the indices to the numbers. That being said, what we more care about is probably how we get from the numbers down to the indices, right? And so we can definitely reverse these steps, right? So if we're multiplying 3 and then adding 60, well, the equivalent of that would be, or the inverse of that would be first subtracting the 60 and dividing 3, right? And so that way we can now just solve for our, we subtract for 60 first, my bad. Oh, I just cleared everything, great. Undo. We can obviously do 213, subtract 60, and then divide it by 3. And you do your arithmetic, you guys know how to do this, and you get 51. So we'd expect this to be 51, and everyone's good. So of course you can see that this is how we're going to be counting lists, right? We're going to be assigning each number an index, and then figuring out a relationship between the index and the the numbers in the list, right? And that's the whole idea of counting lists, right? And one final example before we do some problems. Let's look at problem 1.6. How many 4-digit numbers are perfect cubes, right? Obviously we could count all of them, but again, that's not what this class is about. So we're probably gonna want to figure out, well, if we want to figure out how many perfect cubes there are, we're gonna want a relationship between the indices 1 through something and the 4-digit perfect cubes. So the first thing you could do is think, okay, well, 1000 is 10 cubed, and 1000 is the smallest perfect cube, 4-digit perfect cube, because it's the smallest 4-digit number, and it's a perfect cube. Nothing too difficult about that. Of course, you can, if you're a little as good at your math, you can figure out that 21 cubed is 9,261, and 22 cubed is, who cares? It's bigger than 10,000. It's at least 10,000, so that's not a 4-digit number, right? And so already we sort of formed a relationship here, right? We formed a relationship between the numbers 10 through 21 and their cubes, right? Because these are what we want to count. We've discovered that we have like a sort of it follows a list, and there's already a defined relationship for us, right? The fact that they're perfect cubes means that they have cube roots in the integers. And then from there, you can just use the formula, or you can actually bring it all the way down by doing an add 9 relationship, and you get 12. The point is you get 12. But you guys see how these relationships can get pretty complicated, and obviously these aren't actually that complicated, but it's going to be important to know how to do these as we move along into the future. If that makes sense to everyone, then let's just get started with some problems. So these problems shouldn't be too difficult. Hopefully everyone can do them relatively quickly. So let's work on 1.2.1 to 1.2.7. Let's do those 7 problems. Some of them are going to be easier than others, right? Because the first one's looking really easy. The second, obviously it gets a little harder later on. I'll give you guys 12 minutes to do these. And I will assign people problems to talk about, or just to give answers to. It doesn't matter. And yeah, we'll meet back here at 4:30 exactly. And that's about it. Yeah. If you have any questions about any of the problems, let me know. Again, it's very important that you guys figure out how to do this and figure out this like one thing, like this little relationship between the numbers and between how to count lists and the indexing. Yeah. Sorry. Okay. Okay, let's bring it back. So let's just quickly go over each one of these problems. So I've assigned everyone a problem that they will talk about. If you didn't get to your problem, that's okay. You gotta think about it in the time that it takes to get to you, or you can just give me some ideas if you don't have the answer. But yeah, let's just go. Let's start going in. Ling, do you want to talk us through how you did 1.2.1? Very briefly, of course. These questions you can just go super fast. Just give us a little rundown of how you might have done it, and give us an answer, and that's all I'll need. Okay, the answer's right. And how did you get 58? By the way, this might be a good time for everyone to type their solutions up, just so they can have it ready when I ask them. Okay, so Ling, you said the answer is 58. Do you want to give us a little reason why? Yeah, that would work. So of course you could just use the formula here as well that we kind of created at the end. But yeah, absolutely. If you want to do the little assignment thing, if you list them out from 36 to 93, and you start indexing 1, 2, 3, you'll notice that the difference will always be 35. And so once you get to the end, you can do this for all of them. And so once you do this, once you do this all into the end, you'll just be subtracting. You're subtracting 35 from 93, and then that'll get you 58. Yep, that's right. All right, moving right along. 1.2.2. Aaron. Oops, that looks like a third A there. Like that. You got 64. That is correct. And how did you get 64? All right, so you divide all the numbers by 2, sure, and subtracted by 1. Yep, that will work. So if you want to think about this in terms of indexing, again, these have a difference of 2, and you want to have a difference of 1. So you divide by 2 first, and you go from that to 2 to 65, and then you can subtract 1, and it will be down to 1 to 64. And then I'll get your indexing. Of course, you might want to make sure it goes both ways. Of course, most of the operations we're doing today will go both ways, but just keep that in mind. But yeah, that gets you your answer of 64. Perfect. All right, Rocky, do you want to talk about 1.2.3? Add 3 to each number, then divide by 5. Oh, okay. And then add 7 to 12 and get 9. Okay, that works. I'm just need to make sure. First of all, that answer is correct. You should get 19. So there's a few ways you can do this, right? But like the main issue here is that first of all, first of all, the numbers are increasing by 5 every time. So you're gonna want to divide by 5 at some point. But these numbers aren't great to divide by 5. So what Rocky did is he first added 3 to each of them so that they became divisible by 5, and then he divided by 5. And then finally, he had a negative 6 to 12, and this had difference of 1. So he simply increased it by 7, and he got over to 1 to 19, right? So of course, we can go through each of the steps. Divide by 5, add 7, subtract 7, multiply 5, subtract 3, and that will get you your answer of 19. Yep, perfect. All right. Let's see who's next. Nancy, do you want to talk about? I'm not going to undo everything. Nancy, do you want to talk about 1.2.4? Okay, let's see what you wrote. You divided by 3. And then use the formula b minus a plus 1. Yeah, that works. Okay, so for this one, the numbers are in reverse, but that's okay because you can just write it like this. You can just write it in the other order, and that is perfectly fine. So good call there. Once again, Nancy noticed that there's a difference of 3, so she went for a division by 3, and then 147 divided by 3 is 49. And then at this point, she'd use the formula, which is perfectly fine. Because as long as you understand the formula, I think that's the important thing about this class. As long as you understand the formulas you're using, you're fine. If you start using formulas you don't understand, that's where it goes badly. Because that's where you start doing. That's why you start like extra counting or like not counting what you're supposed to because you didn't like fully understand the premise of the problem. But yeah, that works, and you get 37 here. Yeah, perfect. All right, 1.2.5 Howard. Right, so you saw a bunch of thirds and you weren't happy with them, so you decided to multiply by 3. Okay. So if you multiply by 3, you should get 11, 13, 15, all the way to 81. All right, sounds good, Howard. And from there, what did you do? What did you do? You subtracted 1 to make them all even. I like it. Right, because at this point you probably notice that there we have a difference of 2 going on here. So I'll just fill the rest because we want to move quickly. So then you divided by 2 because you want to get the difference to. Yep, you want the difference to. You want to get the difference of 1, and then finally you can use either the formula or the actual or like reducing it down to 1, and you get 36. Yep, that's correct. Perfect. 1.2.6 then. Whoever has that, Myron. Let me just erase all this. Oh my god, it's all that way. That's fine. Okay. Let's see. Answer 21. Explanation 150 divided by 21. That's actually it. That is a very dangerous. That's actually a very dangerous way to do it. And of course I'll explain. I can explain why. 1.2.6. It does work for this question, right? Because here you're looking for multiples of 7, and it just turns out that that happens to be 7, 14, 21, and you want to go all the way up until you can't, which is going to be 147. And of course, this turns out to be the floor of 150 over 7, as Myron said, because turns out when you immediately here divide by 7, you just get the list 1, 2, 3, and then 21. That being said, you won't be able to do it for a situation like, let's say you want to find multiples of 10 between 11 and 103, right? Actually, no, bad example. 9 and 101, okay? You take if you want to do this, one way you might want to think about this is to take the difference, right? And then divide by 10. You might want to add 1, 2. And it rounds to about 9.3, so you might think it's 9. But the answer is actually 10. Answer actually 10. So this won't always work. Fortunately, it does work for these multiples below something without a lower bound, as long as it's 0. As long as it starts from the actual multiple itself. Yeah, but in general, try not to do it that way. Of course, to do this question, you would just think, okay, what's the highest multiple of 7? That's 150. You'd find 147, then you'd make the little indexing trick and you'd be done. But yeah, sounds good. You get 21. The point is you get 21, and that's what. And looks like you got that. All right. Finally, Charles, you want to talk about 1.2.7? How many perfect squares are between 50 and 250? Oh, he was ready. So since the smallest squares, they're in 50, 64, yep. Right, so you want to find the first squares, the highest and lowest square you're considering, and that appears to be 64 is 8 squared, and 225, which is 15 squared. And from there, yeah, you create a relationship between these through square roots and squares, right? And you get 8 to 15, and then you can do 15 minus 8 plus 1 is 8, whatever you want. But yeah, and you should get 8 here. But yeah, does that make sense? Are we clear on how do we count lists? If we are clear, then we're going to quickly move on to the next part, which is going to be counting with addition and subtraction. So obviously we can't go our whole life just counting because just like going in there and counting. We want to, and we don't want to have to because the way we count it assumes like each one has its own sort of identity, right? But what if we don't care about like the individual, we just care about the group in general, right? Like, oh, I have 20 things. I'm not gonna sit there and draw all 20 things. I'm just gonna say I have 20 of them, right? So obviously you want to be able to manipulate numbers through more than just listing them out. And that's how we're gonna be counting today. So with addition and subtraction on these numbers. So I'm sure you guys have seen the Venn diagram before. If you have not seen the Venn diagram, that's fine. We're going to go over it today, right? So the Venn diagram talks about groups A and B, right? And there are sort of 4 different regions of the Venn diagram. There's just A, and no. There's both of them together, and there's just B, and then there's the outside, which is A and not B. Don't bother, the notation's a bit weird. What this says this says it's A and not B, A and B, not A and B, and not A and not B. Don't worry too much about notation. I just need something to write there. But yeah, basically A and B here are characteristics, right? You can either have them or not. These are characteristics. Characteristics, traits, whatever you want to call them. There are different things you could have, and you could also not have, right? And you can have both of them, you can have none of them, and that wouldn't matter. And so you'd be able to sort things and people like this. So let's take a look at some of these sample problems, right? So at Brown High, let's look at problem 1.7. All right, at Brown High School, there are 12 players on the basketball team. All the players are taking at least one foreign language class. The school offers only Spanish and French as its foreign language classes. 3 of the players are taking Spanish, and 5 of the players are taking both languages. How many players are taking French? Okay, so if we were to draw this as a Venn diagram, right? Where we obviously don't want to, maybe we don't want to list out people, so we're just going to use numbers to talk about how many people there are, right? So we know well, first of all, each one of the 4 regions is going to have a value, right? A, B, C, and D. If there are 12 players on the basketball team, then we should expect that the sum of these to be 12, right? That should go without saying. No student will fit in more than one category, and every student will fit in one category, right? That's sort of like the beauty of Venn diagrams here. Right here we're trying to translate the math the words into math, right? The school offers only Spanish. All of its players taking at least one language foreign class. That means A is 0, right? Because there are no students. I should probably label this one. Let's label this French and Spanish. Right? You'll notice then that A should be 0 because if everyone's taking at least one foreign language class, there can be no one taking no foreign language classes. So we say immediately A is 0. The school 8 of the players are taking Spanish. If 8 of the players are taking Spanish, that includes C and D, right? Only these people are taking Spanish, right? No one else. So that means C plus D is equal to 8. And finally, 5 of the players are taking both languages. Well, that's just C, right? Right. C. This is the only area where both are covered in. All right, I'm just gonna. right? This is a region where you have both. And right, you see how we translate this word problem into an algebra problem. Of course, maybe you didn't want to write all this like algebra stuff out. What you could have done is you could have just gone in and started filling them in yourself. 0, right? You know this is 5. We know this together is 8, and we know the whole thing is 12. Now, however you want to do it, but as long as you, and then from up here, you want to find how many players are taking French. Well, how many players are taking French? What do we want to find? We sort of want to figure out what we're trying to find first, right? Because once you have all the information, it's just up to what we're trying to find. And the answer here is taking French, which is of course going to be B plus C. So note the question is not asking for B, it's asking for B plus C, because that's how many people are taking French. So with that in mind, we can either solve the algebra, look at the Venn diagram. I'll look at the Venn diagram because I don't want to write all the algebra out. 5 plus 3 is 8, and then 0. So then all these should add to 12. So you're just missing 4 here, which means that overall there are 9 people taking French. That's just a quick example, and you can do this with any number of any few traits. You can also do this with 3 characteristics, right? You can have the fable 3, the 3-way Venn diagram, and you'd have the 8 different regions, right? So and of course in 2D when you're drawing this out, you won't be able to go further than this, because the limits of our dimension do not allow for us to put another circle in without ruining everything. But of course, if you can draw it in 3D, which I will not be doing today, but you could have like 4 spheres put in like a pyramid shape, and you could get it like that. Does that make sense? Do we see how Venn diagrams allow us to group people together so you don't have to count them in lists, but it allows us to also reason about them, and how it represents this algebraic little system here? Right, and also do we see the importance of what we're trying to look for, right? Here I could have easily just said, oh, the answer is 4, but the answer is not 4 because we're looking for people who take French, right? Which happens to be the sum of B and C, or the entire red circle here. Does that make sense to people? Do I need to do another example? All right, who wants me to do another example? Just raise whatever, like, use your Zoom or like talk in chat or however you want to. Does anyone here want me to do another example? Because there is another example in the book, and I will be happy to go through it if you need. But if not, then we can go straight to problems. Yeah. Does anyone really need me? Oh, Aaron would like you to go through another example. Is there anyone else who would like to go through another example? All right, sure. Looks like we're going through another example then. Fantastic. So let's go over 1.8 then. 1.8. Let's take a look at it. So first of all, let's draw a Venn diagram because we know we're going to need it. So there are 27 cats at the pound. Great. We know what we're counting already. We're talking about cats. 14 of them are short-haired. Okay, so now we're talking about being short-haired, which means the opposite of that is probably being long-haired. 11 of them are kittens. So now we're talking about kittens versus adults, right? So we kind of have 2 different traits available for us, hair length, right? We have being a kitten, being an adult as under age, and we have having short hair and having long hair as our 2 different, there's another sort of trait, right? And you can see how you can mix and match these, right? You can be a long-haired kitten, you can be a short-haired adult, you can be a whatever. And all of that is represented in our Venn diagram. And so let's take a look. 14 of them are short-haired. Okay. Well, that means that within our short hair, where once again we can do A, B, C, D. Again, it's up to you. We have B plus C is 14. Oh, I forgot to mention there, because there's all the cats, we can say equal 27. We can say A plus B, the overall sum is 27. 11 of them are kittens, right? If 11 of them are kittens, that means it's the blue circle here, which means it's C plus D, and you get 11. And then finally, 5 of them are long-haired adult cats, not kittens. So long-haired, not kittens, that is neither of these properties, which means it's actually the outside we're talking about. Right? This is all that's not short hair and all not kittens, which are long-haired adult cats. So that means what we're given is that A is 5. Right? And we can fill that into our Venn diagram if we want. So at this point, we want to think, okay, and at this point, it might help to look at the algebra for this one, right? So first of all, if A is 5, we don't want to deal with this. I'm just going to quickly get rid of the A here, move it to the other side, and subtract by subtracting 5 on both sides, right? And now we're left with 3 and 3. And at this point, it's up to your algebraic intuition to see what we do next. You could, for example, take this equation and subtract it from this equation, actually the other way, and you'd get B is 11, which would help. You can do the same for 2 and 1 here, and then you'd get D is 8, and then you'd be able to fill in like C is 4. Does that work? No, did I mean C is 3? I meant C is 3. I did mean C is 3. My bad. Right. Sometimes you might need the algebra, so I always like to write out the algebraic stuff just in case I need it, because sometimes you can't just look at it and it's like, oh, obvious, And you put them all in, right? You can put all the numbers in, and you can go back and verify, each one of these, and be like, okay, well, are all the properties satisfied, right? Because if all the properties satisfied, then you did it. First of all, are there 27 cats? 5, 11, 3, 8. Or we can do 5, 11, that's 16, 19, 27. That's good. 14 of them are short-haired. Well, we have 11 short-haired adults and 3 short-haired kittens, which overall means 14 short-haired cats. 11 of them are kittens. 8 of them have long hair and 3 of them are short hair, which is good. And that makes 11. And finally, yes, 5 of them are long-haired adult cats, right? By the way, if you want, you can also if you find it hard to remember, you can on this. I recommend on the side being like, okay, what is A? A is long hair adult. B is short hair adult. I just write it all out like that. And so that way you don't forget, right? Because the last thing you want to do is forget, okay, which one is, this one, right? C is short-haired kitten. And then finally D is long-haired kitten, right? So if you ever find yourself forgetful of these things, just feel free to write it on the side. It'll help you in the long run, especially in more complicated questions. Does that example hopefully clear things up for people? Because if it did, let's do a few problems then. Well, I'll do too many because break is soon, and I would like that to happen. So how about we just have everyone? Everyone do a practice by themselves, right? Let's get 1.3.1, please. I'll give you guys 6 minutes to do it. So that's like 5 p.m. exactly. Right? Everyone should try right? I want everyone to get this, by the way. So hopefully everyone gets it. So we're gonna go over it as a group. I won't pick on anybody, don't worry. Unless you want to do it, then you can do it. But everyone try out this Venn diagram thing. Get a piece of paper, start drawing your Venn diagram out, and see if you can get an answer for this question. Right. So I'll see if anyone needs assistance, feel free to ask. I want to make sure everyone gets this. So don't be shy. Don't be shy. Right. And see you in 6 minutes then. All right. Do people need more time? If people need more time, I'm happy to give people another like 3 minutes just to wrap up. I want to make sure everyone gets this. Does anyone need more time? I'll give you guys like 10 seconds to tell me if you need more time. Sure. All right. Rocky has decided that we need more time. So we're gonna give everyone like another 3 minutes. Yep. So see you guys at 8:03. All right. How did people do? Did some people get answers? If you have an answer, please let's hear it. Let's see what happened. If you don't want to expose yourself, maybe if in case you feel like you got it wrong, you can also private message me it. That also works. So let's see what people got today. Okay, we got an 11. Does anyone else want to take? Okay, we got another 11. Oh, look at all these people getting 11. Okay. Wow, everyone's getting 11. All of a sudden, everyone's getting 11. Myron's getting 1 over here. Okay. All right. Yeah, we got 11. The answer is 11. That's good. So let's just, in case someone didn't get it, let's just quickly go over it. So once again, we will be drawing a Venn diagram. I feel like my Venn diagrams get worse and worse as the day goes on. And so let's read the question. There are 20 cars in my. Okay, we're dealing with cars. Good. All of my cars are red or white. That means this is probably one of the properties of, so we're gonna say red here. 12 of them are red. So if we said this B, C, D, A, we'd already know that B plus C is 12, and we know that A, obviously A plus B plus C plus D is 20. And 15 of them are 4-door. So if we call this being 4-door, then C plus D is 15. And 4 of them are 2-door and white, which means A is 2, right? Because that's the one that doesn't apply here, right? Great. So we can fill that in too. And so it turns out this is actually extremely similar to what happened last time, right? We could take away the A here and then move this to the other side to get 16 going on here. And then we will subtract. Right, we will subtract 1 minus 2, and we get D is 4. we can subtract 1 by 3, and we get E is 1, and we can put these back into 1, and we could get that C is 11, which is what we're looking for, which is good. Another way you could do this problem, well, not another way, but another technique here. Like by this time we were looking for C, right? We know we're looking for C, but sometimes, as you know, we're looking for things like C plus D. You know, maybe we're looking for A plus B for some reason, whatever. You might want to find something that isn't exactly one of the variables. And what you might want to do then is just let X be the answer, and then revolve everything around your answer. So let's take a look at it for this question. But if we read the question, let's think about what happens with X. So first of all, we're looking for 4-door and red. So we're gonna call this X, okay? 20 cars in my building parking lot. That's not really helpful to us, so we're just gonna ignore that for now. 12 of them are red. Okay, so 12 of them are red. Then if X of them are red and 4-door, then we'd expect 12 minus X of them to be red and 2-door. Similarly, if 15 of them are 4-door, we'd expect this to be 15 minus X, and we still have something, and we still have like, and we know this is 4, right, later on. And so at this point, you could be like, okay, well now I'm going to solve for my X. Right, and it turns out in this question it's a little simpler to do that by using the last one, and then you do it out and you get X11, which is also works. So from question to question, you might see that that one of these works better than the other. So feel free to mix and match whichever ones you use. It's sometimes hard to tell which one's easier, honestly. But does that make sense? Yeah, hopefully that makes sense to people. I know some people prefer this way because it's less variables to deal with, right? It's just X, and then you can base everything off of X. So you might like this way better too. You might have already been doing it, I don't know. But yeah, if that makes sense, we will go on break now for 10 minutes. So I will see you guys. So I'm gonna let you guys break until 5:18. And when we come back, we're gonna talk about permutations, multiplication, independence, and stuff like that. So yeah, we're gonna bump it up even more. All right, see you guys then. All right, let's bring it back. So I like to do this at the beginning of every after break. I just want to make sure everyone's like back, you know. So can everyone give me an indication whether they talk in chat or they put up something? Like they put up a little yes or a little no or a little what's up, Myron? How you doing? A little thumbs up, you know, however you guys want to do it. I'm just gonna wait for everyone to all right, let's have a look. Howard, Myron, Rocky, Nancy, Aaron, Charles. I think we're still missing a few people. Who are we missing? I think we're missing Ling and Ruyan. Yeah. It's okay. It's being recorded. Hopefully they're around right now. Ling, Rin. Ling's here. All right, fantastic. Yeah. Rin came in late, so I don't know what's going on over there. Okay, everyone's good. Fantastic. Okay. All right. Let's talk about the next topic, which is going to be multiple events. But before we do that, a little quick thing. Okay. So actually no, we can start with this. So let's talk about counting multiple events. Okay. So remember when I gave you the initial example before, when I gave you like the triangle, circle, diamonds, whatever, and then I put like another copy of it below it, but this time I shaded it in, right? Well, what I really did here was actually do counting multiple events, right? Right here we established that there are 5 times 2 equals 10 of different things. But what I could have done is I could have said pick a shape, right? Pick a shape out of those 5, and then pick a color, black or white, right? And so obviously picking a shape out of these 5 gives us 5 choices, and picking a color between black and white is 2 choices. And so now, of course, you might think, oh yeah, just multiply them, and you'd be right. That is how you do it. But there is a right. If you, for example, if you look at problem 1.9, right? How many? You have 3 shirts and 4 pairs of pants. How many outfits consist of 1 shirt and 1 pair of pants can you make? It turns out that the answer is 3 times 4 is 12, right? Because you can pick a shirt and then pick a right, and then pick a pair of pants, right? So key thing to know here, the word "and" in counting and probability suggests multiplication. But it's important to notice that it's not always going to be right. If you have, well here, if you have to pick a shape and pick a color, right, then you're saying, okay, I gotta do this and then this, right? If I'm picking a shirt and a pair of pants, you know. But there's a small tidbit, okay? So let's say we had 2 events, okay? Raining or not raining, okay? Obviously, I can't choose this. I obviously can't choose, right? I can't decide, oh, it's gonna rain today. I'm not some like weather god or whatever. And you know, sometimes I like to go on morning jogs, right? So on some days I'm gonna jog, and on some days I'm not gonna jog, right? And so you know, you imagine if it's raining, I might not want to jog. If it's not raining, I still might not want to jog because I'm lazy. But if it's not raining, I might also want to jog, right? Because it's not raining. However, if it's raining, I'm not gonna jog. So I probably shouldn't have done that. Probably shouldn't use X's here. It's bad. Make these check marks instead. Right? These are all possible. However, we still might say, oh, you know, but there should be 2 times 2 is 4 choices, right? Because raining, not raining, that's 2 choices, right? And not jogging, that's also 2 choices. So there should be 4 choices, but there's only realistically 3, right? And here, and this is the issue of independent. I shouldn't have gotten rid of that. Excuse me. This is the issue between independence and dependence. Okay. So here the issue is that raining and jogging are not independent. They are dependent on each other, right? It depends on the rain whether or not I might jog, right? It depends. But for independent, when you go back to our shirt and our pants, right? Assuming you don't have senses of fashion, right? It doesn't matter what shirt I pick when I pick a pair of pants, right? This is of course assuming you don't have a fashion sense. Some of you might disagree with this. But you hopefully see the difference here, right? There are certain, we call these events, by the way. These are events, right? The event of raining, the event of jogging, right? These are all what we call events. And some events are dependent on each other, right? So, right, you know, if it's raining, I'm definitely not going to jog. But if it's not raining, I might jog, you know. But for something like shirts and pants, it doesn't matter. If I pick the red shirt, I still have 4 choices. If I pick the blue shirt, I still have 4 choices. If I pick the green shirt, I still have 4 choices. So that's what's very important to keep in mind here. And so obviously for independent, and so of course this is something called the law of independence, which you don't have to know. But basically, you can multiply. That's the point. You can multiply. I'm gonna make this more legible because I've been writing pathetically today. You can multiply, right? If 2 events are independent and you want to pick one from this and one from this, if they're independent, just multiply, right? But of course, you need to make sure that it's actually independent. before doing it, right? And so this is where, and so the question is, what if it is dependent? What if it is dependent? How should I find the number of choices that I have if it matters? And the answer is with trees, right? And so I'm gonna draw a quick tree for for our jogging and raining thing, right? So it could rain and it could not rain, right? If it doesn't rain, then I could jog, or I could not jog because I'm lazy, right? But if it rains, I only have one choice of not jog, right? And so we'll be able to count the number of things that go on by counting the bottom of the tree or the leaves. We call these the leaves of the tree, right? Because they're like at the tips of the tree, like a tree. You guys have seen trees before, right? Who here has seen a tree, right? Like if I draw a tree, there are leaves at the tips, right? And that's why we call them trees. Anyway, Myron has not seen trees before. I'm sorry, Myron. I know quarantine isn't bad, but get outside, my guy. But yeah, trees, and we call these leaves, and so we can just count the number of leaves in our tree. No, he's not going outside. Okay, fine. Obviously, if they're independent, your trees will kind of look like this, right? They're just gonna be the same old thing, and they'll all look the same. That's pretty boring though. But yes, we can use multiple. The whole point is multiplication. We can use for independent events, and if they're dependent, we need other methods. And trees are a great way to organize the ideas, as well as get an effective way to do it. But there's a specific type of dependent problem that we want to talk about today as well, and that is problem 1.12. So can we please direct our attention to problem 1.12 in the book? It says, how many ways can I arrange 4 different books on a shelf? Okay, so what I gotta do, right? If I think about my order of steps here, right? When I have a counting problem, I want to break it down into different steps. I want to pick the first book, right? And then I want to pick the second book, and then I want to pick the third book, and then I want to pick the fourth book, right? These are our apparent choices, right? So, all right, let's think about it. How many ways can we pick the first book? Well, there are 4 books, so 4, right? Okay, how many ways can we pick the second book? Well, it's not 4 because it's not 4 because we've already put a book down on the shelf, right? And so you might think, okay, well, here it's clearly dependent then, right? Right? If I have book A, B, C, and D, right, and I put A, right? I put A here. I'll have B, C, and D. But if I put B, then I'll have A, C, and D. These are different, right? Different, right? However, what's important here is that the number of books left is the same, 3, right? And it doesn't matter which book we pick, C, D. We'll always be left with the same number of books for our second step. So even though it's not independent, this is not independent, right? You guys is not independent, right? Because these are different like circumstances. But the number of books is independent, right? No matter what choice you make for the first book, you will have 3 choices of book for the second book. Does that make sense? And if that makes sense, then we can still multiply, right? We can still multiply. You can think about the tree. If you think about the tree, you'll still have those 3 branches. The tree doesn't care what the branches are. But it might have different, like it might have, like if I draw the tree, right? These branches might have different colors, right? At the end of the thing, right? This might be red, blue, and yellow, but this might be red, blue, and green, right? But in the end, we're still counting 6. I still see 6 leaves. 1, 2, 3, 4, 5, 6 leaves, right? So do you see how the tree sort of tells us that we don't need, like, even though these events are not independent, because the number is independent, we can still multiply, right? And we can still keep going like that. We'll have 2 choices for the third book and 1 choice for the fourth book, and of course you can verify these are all the same, and then we'll multiply them together and we get 24. So that's all nice and dandy. Right? The choice, right? So are we clear on the difference between the choices? Like the actual like choices left are not independent, but because the number of stuff is independent, we can still multiply. This is absolutely critical. This is absolutely like essential for you guys to know. So I hope everyone is understanding this right now. I know, as in I want someone to confirm, I want people to confirm to me that yes, they understand the difference between independence of choice and independence of number. I want to see this. I want to see a yes in the chat. I want to see something. Sure, yeah, okay. I'm liking what I see so far. Yes, good. This is good. Barry, do not forget this. Thank you, Myron. Myron always respecting women. All right, if that's cool, then we can talk about this. So this sort of occurrence happens a lot, right? This whole idea of, oh, I put one thing away and I don't have it as a choice later on, and we call that a permutation, right? And so a permutation is pretty simple. I have n things, and I want to order k of them, right? Order, like as in like, I want to put them on a shelf like the books. I want to put people in a line. I want to whatever, right? Or if I want to order k of them, then, well, if we do what we did before, right? Our first choice of thing will have n possibilities. Our second choice will have n minus 1. Our third choice will have n minus 2. And let's go all the way down to the kth one. And eventually we'll have n minus k plus 1. Again, hopefully from earlier today, we looked at our list. Hopefully we recognize why this is n minus k plus 1. And of course, we then multiply them together, right? And we call this the permutation. The permutation. And we sometimes represent as npnk, sometimes npk, like that. There's a whole bunch of ways. To express it. And right, it's just gonna be this formula here. It's gonna be n times n minus 1 times n minus 2, all the way to n minus k plus 1. And then, of course, what ends up happening mostly out of permutations, most of the times we also want to order n of them, right? We just want to order all of them. And it turns out if you do that, you're going all the way down to 1, right? You're multiplying them all together. This is so special, in fact, we have a name for it. It's called the factorial. Factorial. Right? And the factorial, what it represents is the number of ways you can order n things, period. Right? Order n things amongst themselves, assuming they're all different. You have n factorial ways. If you have 4 things, boom, you have 4 factorials, 24 ways to order them. Simple as it gets. Little tidbit, a little important, 0 factorial is 1. If we think about the definition of factorial, this is what it means. How many ways can I order 0 things amongst themselves? 1. You don't order them. That is the logic behind it. So yeah, it's not 0. This is not 0. Don't think of it as 0. It's 1. Okay. 0 factorial is 1. Get it through your heads. Yeah, that's about it. Fantastic. Does that make sense to people? Right, we got a few definitions here, right? Very important definitions. Write these down somewhere, maybe. Permutation and factorial, right? Factorial, it represents multiplying all the numbers up to 1 from it, and permutation, you stop somewhere, pretty much. Does that make sense to people? If it does, let's do some questions. So I kind of did 1.4 and 1.5 together because I felt like they were pretty much the same thing. But right, just remember that if you want to order all the things, use a factorial. If you want to order some of the things, use a permutation. Pretty simple, hopefully. Okay, in that case, let's do some math problems. All right, we have 25 minutes left, so I'm gonna give you guys. Ooh. All right, here we go. Let's do 1.4.3, 1.4. 9. We'll be doing both. We're doing 2 different chapters, by the way. 5.1. All of them. A, B, C, D, E. Oh crap. Let's say 1.5.3 is really good. All right, 1.5.3, all of them. Let's do those for now. I will give you guys. Damn, wait, 1.4.9. Oh, 1.9 has parts too. Hey, I forget 1.4.9. Don't do 1.4.9. We don't need that. Yeah. Don't do 1.5.9. Just do these. I think these are pretty sufficient for now. If you guys want, you do 1.4.4 actually. Yeah, it's up to you. But yeah, do those problems. I'll give you guys. Yeah, actually for 1.4 5.1, you skip B and E. I just want you guys to do the yeah, skip B and E. Skip B and E for 1.5. I'm sorry I'm changing this so much. Skip B and E for 1.5.1. Yeah, that is good. Yeah, so I'll give you guys, let's say 15 minutes. So work until 8:52. Oh, damn it, I'm Eastern time again. Jesus, 5:52. Yeah, and we'll see you guys back here momentarily. I don't know if I'll have too much time. I'm sorry if we go overtime today. I want to get all these questions through. So let's go quickly when we get there. Oh, by the way, if you guys are ever done at any point, like if you guys have finished all the problems, feel free to let me know. Feel free to give me your answers as well. Just so I can verify to see if you're doing anything wrong, so you're not like wasting time. If everyone somehow finishes all the problems in the next 15 minutes, then we can just start early. Yeah, that's about it. I should have mentioned this before, but for 1.4.3 and 1.4.4, don't bother getting the actual number. If you leave it in like something times something squared times divided, whatever, that is fine. Yes, that is all. Thank you. I just assigned questions, so if you haven't gotten to your question, you may want to prioritize that. Just FYI. All right, let's get back together. So again, if you want to speed up the process, if you could type up your solution ahead of time, that would be very helpful. It looks like Rocky's he's already done. Fantastic. Okay, so let's start. 1.4.3. Rocky says there are 26 letters in the alphabet. That very impressive, Rocky. Good job. And two slots of letters instead of 10. Right. So each one of these letters and numbers are their own choice. Okay. So right, if you have like number, what's that? Letter, number. Right. Each one of these represents their own choice, and there are 26 letters and there are 10 digits. Yeah, I don't know what says numbers. You should say digits, but okay, that's fine. And so each one of these is independent of each other, right? If I choose B for this one, it doesn't change what the second letter can be. Similarly for everything else. So we can just multiply them together, and you do get 26 squared times 10 cubed, or 676,000. All right, good job, Rocky. All right, Howard, 1.4.4. It's a pretty similar question. So let's see what you got. So since you can choose two letters, there are three letters, Howard. Howard, it's all good, all good. Yeah. I know what you mean. And you choose two even digits, right? And there are 5 even digits, by the way, guys. 0 is even. It's not a number theory class, but yeah, 5. These are even. It's cool. Yeah, I know. Some people don't think of zeros even, but that's cool. That's cool. But like, you still have the process down, right? Like, as long as you get the process down, it's okay. Howard, you got to keep going. 2 odd digits, right? 5 of them, right? And you 1 3 5 7 9. Right. And so once again, none of these choices affect the other. So you can multiply all these together and you get some godforsaken number. And apparently, for those who are interested, it is 10,985,000. Just FYI, that is this number. Yeah. So that's how you do those two questions. Right, good work. All right. Not 1.415. That is not right. 1.5.1. I'm just gonna erase this part first. All right. Question A. Does Charles want to talk about how he did 1.5.1a? Okay. Permutation of 8. You meant 3. It's fine. You got the right answer. Right. So one way you can think about, actually, this is a good. So thank you for bringing this up, Charles. So remember, if you recall, that from if we do 8 3, it's mostly the first 3 numbers going down. But we could also just say that I had the original all of them, but then I divided by the rest of them. So another way you can define permutation, if you're interested, is just n factorial over k factorial, which will probably be more easy for you to remember than some of the other stuff. But yes, you do this. You obviously don't need all of this, and you just find 8 times 7 times 6, which happens to be 336. All right, well done. Aaron, we're going to talk about C. That's okay. If you don't feel like you can explain too much for this one, it's because you can't. You kind of didn't get that far. All right, well, well, take a look at the question then. We're looking for P of 31. Do you have any ideas as to what this value might be, just looking at it? It's okay if you don't. You can just say so. Yes, 30. By the way, I would not use stuff like exclamation marks and question marks and other sort of other things, because you might, especially in number, especially here, because you might actually mean 30 factorial. It's okay, I know you mean 30. But yes, 30. That's correct. It is one number from 30, so this one's just a vibe check. Also interesting to note is that n permutation 0 is defined to be 1. Please keep that in mind. That again, this has to do with, like, oh, doing nothing is a thing, so just keep that in mind. D, Ling, do you want to talk about 6 choose 6? I want to say choose. You got, for those of you who know things, I keep saying choose. Permutation, P of 6 5. Ling, do you want to talk about how you did P 6 5? Yeah, that is right. So you just you can plug in the formula, whatever. You do get everything 6 times 5 times 4 times 3 times 2, which is just 6 factorial, actually, because you kind of times 1 there. 6 factorial, which if you guys have memorized, by the way, I highly recommend memorizing the first 6 factorials, just knowing them off the top of your head. They're not hard to remember, I promise. So just keep them, just remember them. They're really helpful to know. All right. Good work, guys. Finally, 1.5.3. The hardest problem of the set, probably, of this little. All right. Myron, let's hear what you got for A. If you got there. 1,320 is correct. So, if every ball remains outside the barrier, so first of all, once again, we want to think about our choices here. We're choosing a first, second, and a third ball. The first ball, of course, we have 12 choices, right? We have there are 12 balls in there. But it doesn't get replaced. So afterwards, we still have 11 choices, and the third one we have 10 choices because now there's 2 balls missing. Again, take note that the number is independent, but not the event, right? The number of balls will always be 11 afterwards, but of course it might be a different 11 balls every time. But again, that's what, again, for multiplication's sake, that is fine. For a tree's sake, you multiply them together, you get 1,320. All right, good work. Nancy, do you want to talk about B? Since there are 12 also, yes, okay, good. So this time, we are actually not putting them back in. We are putting them back in, so we're always drawing. We always have 12 possible drawings every time. Note here that the event is also independent here, but that's not important because as long as the number is independent, it's fine, right? But here it's important to it's cool to recognize at least that the event is independent, right? Because no matter which ball you take out for the first one, you're putting it back in, so you have the same pool no matter what the first pick was for the second and third pools. And yeah, that's right. And finally, C, Ruin, if you did this, obviously this question's pretty far away, so it's okay if you didn't do it.
Yeah, I got it.
Okay.
I've basically done all this in school like a year ago.
Oh, I see. Okay, it's okay. So you'll be like asleep for the first few chapters, man.
Okay, so basically 12, 12, 11, which you get 1, 5, 8, 4.
Yeah, that's correct. So in this case, it's a little weird, obviously, but in this time you're putting it back after the first draw. You have 12 for that. So you still have 12 for the second draw, but now you're leaving it outside. So you have 11. Once again, here these events are independent, but these are not event independent. I should say event dependent. Right? You multiply them together. Again, the numbers are all still independent. So you can multiply them to get 1,584. Yeah, okay, looks like you guys have a good handle on the basics then. And just in time too, it just hit 6. So here's what's gonna happen now. Don't leave yet. I have some problems ready for homework. So there will be 7 standard homework problems and 4 challenge problems. The challenge problems are optional. They're not worth. You won't get any points if you do them. However, they are a good exercise, and I highly recommend it to anyone who thinks they understand the material well enough and has the time to do it. Some of these problems I will ask you to show your work. I will write PSYW. Please show your work on them. Please show your work for them on your homework. If there's any step that might be like confusing, like obviously if there's arithmetic, I don't care if you know how to do 12, if you knew how to do like the 10 million thing, 10 million that we just did in this class, I don't care if you did that. But I care about, do you recognize things like independence? Do you recognize, oh, yes, I can multiply here, or no, I cannot multiply here, or yes, this is an ordering, so I'm going to use permutation, stuff like that. That's what I care about. So please show your work in that regard. Right, show your final, at the end you should have like a big math expression of a lot of multiplies and adds, and then you can just skip right to the answer if you want. That's fine. But yeah, please show your work on some of them. I won't ask you to do for all of them. For the ones you don't have to show your work, feel free to just put the answer. If you get it wrong though, I don't know how many points I can give you because I will give partial credits. So you may also want to show your work for the other problems as well. That's about it. We will also have quizzes after a chapter. We will have quizzes on it. So expect next week we start with a quiz before moving on to chapter 2. It's the quiz. I won't like keep the quiz on. It's just to refresh our memory on like what we just did. So yeah, hopefully that it's not supposed to be a stressful time. But yeah. Are there any other questions about what we just did today, or anything for that matter? Because if there are not, you are free to go at this point. Yeah, stay tuned for homework. Please do it. That's about it.
So
I will stick around.
Post that on Google Classroom?
I will post it on the Google Classroom. Yes, within like 2 hours. Let's say I will post it.
Okay.
Yeah, so check that out. If you have any questions about the homework at any time, feel free to just private message me there. I'll be happy to answer. Sometimes, I won't always be. I'm not gonna be on there 24/7, but I'll check it every now and then. But yeah, I'll stick around if anyone else has any more questions regarding the material or anything. But yes, thank you for coming. See you next week. Okay, so what is homework? I will post that, Rocky. I will post that in 2 hours on the Google Classroom. So yes, so look forward to that. Yep. It will be due before class next Tuesday. And everyone's gone. Yeah.